Okay, so how is everyone today? So what's your question?
Good. Well, I guess I was just wondering about um, will there be any more homework due? Will we? The final is Wednesday, right?
That's right. So there's not going to be any more written homework due. There will be further written homeworks posted, and you can consider those to be like you should know how to do this for the questions which are on the final exam that you're seeing for the first time. There won't be any further of these turned in. So today, all of them are graded except these, obviously, and those you'll be able to download them and all that today. The scans, I mean. These will get done as well. I'll get them to the graders as soon as possible, and I'll tell them to do it post haste. I'll start posting keys for the things that have not yet had a key posted. The final exam is Wednesday morning at 8 a.m. I'd like to mention that I didn't make that choice. The registrar did. And it's been that way for at least 2 months. Probably more like 10 weeks or more. And
That's in this room?
it's not in this room. It's in a different room. I'll send you a message. But it's in a room on campus. So don't take me, don't take this as it. But if I remember correctly, it's in the green building. I don't mean the building which is green. I mean the building that is named green. It's over there. So I'll send you a message. It would be good of you to figure out where that room is before the fact, right? In the sense that it would not be good for you to be wandering around trying to find it when it's going on.
We have 2 hours.
In fact, more. You have 2 hours and 45 minutes. So you should not feel pressed for time. So I understand that some of you felt pressed for time for the midterm. Okay, but that was 50 minutes. So the midterm was. The final exam is 165 minutes. So more than 3 times as much. Yes?
So I know that we can make up any quizzes or like this homework on the exam, but how many questions do we
So,
do?
right. So the redo portion is going to consist of all of the out of 10 questions that were not on the midterm. So the ones that were on the midterm were like up to and including 1.8 or 1.9 or something like that. I don't.
192.
One, okay. So then that would mean the things that start with 2 onward that were graded out of 10, you'll have a chance for those. There were 3 questions on the midterm that were graded out of 10 that were new. You'll have a chance at those. And if there's so this is now an if there's enough time for me to do everything else, I'll try and put a redo for all the ones from the first half. But if it can't be done, then it can't be done. I haven't figured out if it can be done yet. Then beyond that, there'll be some questions. So all of that I just said, that's all optional. It's the redo part. Then I think your question was, what about the part that's not redo? The part that's not redo, well, let's consider. That right there is 3.6. That last one. So then that means that the lectures which have no homework turned in are 3.7, 3.8, 3.9, 4.0, and I think today is 4.1.
Yeah.
So that means that there's going to be 5 questions that aren't redo. Now they won't be like surprises because. Not at least not entirely, because those are the ones I'm going to post homeworks, and you're not going to turn those in. They're not for turn in. You should be familiar with this before you get to the exam. That's those 5. Then in addition to those 5, I'll probably make another 2 or 3 that are somehow comprehensive. Just like the 3 that were on the midterm. ish, followed by a multitude of redos. Other questions? Yes?
Is there a limit to how many readings we can do?
Again, I'm going to have to check that because in the end, I only have so much labor allotted. It's probably going to be close to 10 again, because that's probably about the cap. I can't ask the graders to do to move the heavens and earth. Other questions? Okay, good. So last time we were talking about compositional inverse and identity. So to remind you of that kind of thought, to bring us back into that kind of thing, I'll ask a much simpler question. For each pair of reals, determine if they are multiplicative inverses. Okay, so then the first pair, 13 over 14 and 14 over 13. The second pair, 2 over 5 and negative 2 over 5. So for each pair of reals, determine if they're multiplicative inverses. Okay. So how do we make that determination?
They multiply together equal.
Okay. So 13 over 14. You take the pair and you multiply them together. Now wait, why are we multiplying them and not like I don't know, adding them? Because we're asking about multiplicative inverse. So you multiply them. Notice that the 13s will cancel, the 14s will cancel. And when you've done that, you get 1. And the reason why 1 is significant is because you were starting to say it's the multiplicative identity. So what's the conclusion about this pair? Are they multiplicative inverses? Yes. The answer is yes. Okay, what about this pair? They're not. Okay, but at any rate, how do you confirm or deny it? Well, same as before. So we'll take those two numbers and multiply them. You get negative, and then the product of the numerators is 4, and the product of the denominators is 25. So what's the answer to the question? So the answer is no. Well, why not?
Negative 4 over 25 is not 1.
It's not 1. Okay, so then, but wait a second. If I add these together, then I get 0.
0 is the additive identity.
Right. So what I want you to observe is that this is kind of like it is just slightly a trick question, right? Because I'm asking about are they multiplicative inverses? And the answer is no, but they are additive inverses, right? So, okay, good. So here's a different question. Determine if the following functions are compositional inverses. So F is, let's think about it here for a second. I gotta think. X minus 6 divide by 5, square that, subtract 3. Yeah, that'll work. So that's the first one. The second one is 5 multiply square root. Inside the square root is x plus 3, and outside is plus 6. Okay, so determine if the following functions are compositional inverses. Now, before we get going on this, I want you to see the very loud similarity between the previous question and this one. Right? Here, it was I gave you two things of the same kind. They're both reals. And then I asked, are they multiplicative inverses? And the way you address that question is that you multiply them and check for the multiplicative identity. Right? So now I've given you two things of the same kind. They're both functions. And I'm asking if they're compositional inverses. So what are we going to do? We're going to compose them and check for the compositional identity.
Let me ask you this. I mean, when I look at it and after looking at the notes,
Mm-hmm.
I don't see the ID anywhere. Like I mean, so doesn't it have to have ID written to be the multiplicative, the compositional inverse?
Okay. So, to address that, there was a time when when this question above looked like this, right?
Yeah.
Like that. And at that time, 1 was not written.
Right, yeah, I got it. That's a good thing. Yeah.
So you had to determine whether or not it showed up. The fact that it did show up for this one means the answer is yes, and the fact that it did not for this one means the answer is no.
Gotcha.
So we have two things of the same kind. We have two functions. We're asking if they are compositional inverses. So what we're going to do is compose them and check for the compositional identity. If I had been asking if they were banana inverses, then we would want to banana them and check for the banana identity. And that's just generally the structure of this question. Okay, so we'll compose them. So f composed with g, evaluate at x. All right, so how do we write this without the composition operator? F of g of x. So we're going to do that. All right. So now I'm going to consult f's formula and say, okay, in its formula we named the input x, and now I'm going to figure out all the places where x appears in its formula. That one place. So now I'm going to copy f's formula exactly, but everywhere I see an x, I'm going to write an empty set of parentheses. So I'm going to copy f's formula, but everywhere I saw that variable, I'm going to do this. So I wrote that empty set of parentheses. Then what gets written in those empty parentheses?
G of X.
G of x.
Now, when we're doing this, do we need to include that step where we actually first write g of x, or is it okay to go ahead and, I understand absolutely why you're doing it, but that doesn't necessarily need to be included.
I'm going to write one more step, then I'm going to address. So, all right, then, so now that we have this step, then now I can copy what g does. So like this. So now g does that. 5 times the square root of x plus 3. And then add 6 on the outside. Subtract 6, divide all that by 5. Square it all, subtract 3. Okay. So I think your question was, can I go? Can I somehow skip to this one? I think was the question. Okay. So here's the thing. If like for example you did exactly that, that'd probably be okay. That'd probably be okay. Probably. But here's the problem with it: is that there's two problems. The more steps you skip, that means the more stuff you're doing in your head. Now, the first problem with that is that I can't grade what's in your head. That's the first problem. The second problem is that if you skip from here to here and you make a mistake, that is indistinguishable from you having no idea what you're doing. Whereas if you show the intermediate steps and you make a mistake, then I can say, well, probably pretty much knew, but then, you know, I can see the mistake was right here. So, you know, in the end, you know, I can kind of say, like, you know, it's sort of like the question, should I wear a seatbelt?
Yeah,
Yeah, probably. It's probably a good idea. Okay. All right. So now that we've done this, again, we're checking if there are compositional inverses, which means we're going to do a bunch of simplification now. And what is it? What would we need to simplify it? What would it need to simplify to for us to say yes? It needs to simplify to just x. Okay, so let's do it. So these square parentheses, they can be omitted. They can be dropped because of the associative property, and then after you drop them, what cancels? The 6's cancel. All right. So the 6's have been canceled. Now what? Fives cancel. And for the to just short circuit any question, do I want you to see? Do I want to see all of this? And the answer is, yeah, I want to see it. I want to see all of the. Okay, now this cancels. Okay, now that cancels. All that. Okay, now what? The square and the square root cancel. Now what? Right, the parentheses can be dropped because of the associative property, and then
You get X.
the 3's cancel, and we get x. So what I want you to see is that, in a sense, this is the composed machine in all of its glory. It's saying that, okay, well, I want you to take an x, add 3, compute square root, multiply by 5, then add 6. And after you've done that, I want you to subtract 6, divide all that by 5, square it all, and then subtract 3. But doing that is the same as doing nothing, right? If you do that with 10, then the output is 10. If you do that with 0, the output is 0. If you do it with any x, the output is x. Okay, so that means that this function is doing nothing. It's just passing the x along. It's like a conveyor belt, which the conveyor belt is the identity function. So does that mean that they're compositional inverses?
We don't know yet.
We don't know yet.
We're not done.
Why? In what manner are we not? Why are we not done?
We have to know g of f of x is also.
All right, we got to do it in both orders. Both orders. The reason why you have to check both orders is because composition does not commute. It's not necessary to check both orders for additive inverse or multiplicative inverse because add and multiply commute. So it doesn't matter what order you do them in. But composition does not commute. So g composed with f, evaluate at x. Writing that without the composition operator, that's g of f of x. Again, taking g's formula, having a look at it, and determining, okay, where all does x appear? Just in that one location. So I'm going to copy g's formula exactly, except everywhere that I see an x, I'm going to write an empty set of parentheses. And then f is what goes in that empty set of parentheses. Okay. So that's the composed machine. And the question is, in the end, can we perform some sequence of algebraic simplifications and arrive at x? So, in the first place, again, because of the associative property, we can drop these square parentheses. So if we drop them, then what cancels? The 3's cancel. So the 3's cancel. Now we have this. So x minus 6 over 5. Square that. And then add 6. Now what? They don't. The 5's don't cancel. At least not yet. Okay, I don't dispute that, but yeah, we got to figure out what. I don't want to commute too many things into different orders. I mean, I agree that I could somehow smuggle the 5 out right now, but what I want everyone to see is that at the present time it looks like this. So the question is, what happens? What becomes of the square and the square root? So I think what you're saying is you want me to write this.
Is that misstated to say that they cancel each other out?
They do not cancel each other out.
You have like a negative something squared, and because it's squared, the result will be positive, but you can't always ensure that
Right.
there isn't the fact that it's squared.
So what do I need to write here? Absolute value. But now wait a second. Am I being arbitrary and capricious? Because didn't we do the exact same thing over here? Oh yeah, it's different over here, right? It's different over here because notice that on this one the square is inside the square root, and it's the other way around for this one. So this on the left side, it really does cancel. It really does. But that is not the case over here. Now, to sort of address your concern, one simplification you can do with the absolute value is, because it's the absolute value of a fraction, I can say that this is 5 multiplied by absolute value of numerator divided by absolute value of denominator, and then add 6. And then, well, what's the absolute value of 5? It's 5. So in fact, these 5's do cancel, as you say. And then this is absolute value of x minus 6, and then add 6. And now the question comes to, does that simplify? It does not. This does not simplify to x. So what's the conclusion about these two functions? They're not compositional inverses. Okay, so a little bit of discussion is warranted, I think. So for those of you who just like to, take that time-honored human tradition of the thing that we all love to do most, nothing, right? If you want to do that, well, if we had known that this was going to happen on the right side, then we could have done it first, right? Because if we did it first, there'd be no need to even do the left side, right? So if you could have somehow known that, you could have gotten away with about half as much work. Okay. Second is let's consider for a moment the function, calling this y and considering the equation y equal x. What does the plot of y equal x look like? Right. It's a line of slope 1 through the origin. So if you were to plot this one, it would look like this. That's what it would look like. Whereas saying y equal to this one, saying y equal to that one, would it look like this? It wouldn't, right? For a variety of reasons. The most notable one being what you said, that the characteristic shape of absolute value is a v. So somehow this one would be a v. In fact, what it will be is that you could take an axis, and I'll draw exactly this line, but dashed. And what it will be is that over here at 6, because 6 is in a sense, the place where the interruption occurs. Over here at 6, it will be that line, and then like that. So are these two the same? They're not the same, right? So visually, in a sense, these questions are kind of coming down to that if you had these two functions and you compose them in this order and you plot the result, it would look like that. But if you take these two functions, compose them in that order, and plot the result, it would look like that. So then the question becomes, do they both look like this one? And the answer is no. So they're not compositional inverses. Even more concerning or notable is that notice that they are inverses in this order, but not in that order. For those of you who are just loving this discussion, maybe a guy can hope. What the way you say that is that f is the left inverse of g and g is the right inverse of f, but not vice versa. Or you can say that f is the post inverse of g and g the pre-inverse of f, but not vice versa. And that sounds really technical, but I claim that you understand what I'm saying completely, because there's plenty of things that we do in normal everyday life that there is things that are post inverses but not pre-inverses. So, for example, maybe it's the case that tonight you're going to make dinner, and then after you've made dinner, you need to reset the kitchen, otherwise you'll get ants, right? So you got to clean up the kitchen. So cleaning up the kitchen is, in that sense, the inverse of making dinner. But what would you say if I told you this? I say, you know what? Actually, tonight I'm planning on having some company over, and I'm going to make dinner. And we're gonna have a bunch of wine and beer and stuff. And I know I'm not going to feel like cleaning the kitchen, so I went ahead and cleaned up the kitchen this morning, so I don't have to do it tonight. Does it work that way? It doesn't work that way. Yeah, that would be terrific, wouldn't it? But it doesn't work that way. Cleaning up the kitchen is the post-inverse of making dinner. It is not the pre-inverse. So what I want you to see is that it might have been unexpected for this to happen, but I hope it's not unexpected now. That's like saying, first I'm going to make dinner, then I'm going to clean up the kitchen. Those really are inverses of each other, but not the other way around. Yes?
So, for like the final,
Mm-hmm.
if we're doing a question like this and we compose it and we come to find that, like you were saying, if you did like half the work and you found that they're not inverses, do we still have to do it the other way around?
No. If the question is exactly thus. Given two functions, determine if they're compositional inverses. If you're comfortable enough to be able to see, they're not in that order, do that order first and stop there. Yeah. Other questions?
It is irrelevant if they equal the same if they both don't equal x.
Right. That was my question.
Yes, that's right. If it had so happened that they were both this, then the answer would still be no, because they both have to be x. Because getting to x means that it's a conveyor belt. It's just x is in, x is out. Yeah. Okay, so now we're finally at a place. You remember that little clicker thing, my satirical clicker here, where every time I talk about square and square root, now we can finally dispense with it. So on the previous page, we used the following. We said, if you square x and then square root, what do you get?
Absolute value.
You get the absolute value of x. But if first you compute square root of x and you follow that up with square, what do you get? You get x. And that's a little bit disturbing. But let's now we have enough information, enough knowledge and experience to say exactly why it must be this way and no other. Because if you consider this one, you square first and then square root. Well, can you remind me, what's the notation for the punctuation for exponent? Caret, right? So we're going to give x as the input to the caret 2 machine, and then out comes the x squared. That's what comes out. And after we give it to the caret 2 machine, the squaring machine, we're going to provide that as input to what machine? The square root machine. And then out comes the absolute value of x. The reason it has to be this way is because, well, if you put in a 4, you're going to square it to get 16, and then you're going to compute the square root of 16 to get 4. But if you put in -5, you're going to square it to get 25. Notice that the result is now positive. And then you're going to compute the square root of 25 to get 5. So -5 went in, +5 came out. That's why it has to be this way. Whereas, if we look at this one, squared, which machine is visited first? The square root machine is visited first. Exactly this. So the square root machine is visited first, so that the output of it is the square root of x, and then that is now the input to the squaring machine. And now I'm going to write absolute value of x because that is correct. But now I'm going to explain to you why you can simplify that absolute value of x to just x. So for this machine, the machine that visits the squaring bit first, notice that this first part of the machine, what kinds of x will this first part work for? Will it work for negative x's? Can you square negative things? Yeah. Will it work for 0? Yeah, you can square 0. Will it work for positive things? Yeah, you can square positive things. So this works for all kinds of x. It works for negative x's, it works for 0, it works for positive x's. Any kind of x, for the machine, when you put them in this order, any kind of x can serve as input. Now, when you take the two subunits, squaring and square root, and you reverse their order, and you consider the first leg of the machine. Now, for this new machine, the first phase, what x's work? Positive and 0 only, right? Works for x which are greater than or equal to 0, which is to say that 0 works, and so do positive x's. So that means that negative x's are just not in the domain. If you were to attempt to put a negative in to this machine, it would blow up. It would just there'd be no output in the sense that it just explodes. So what I want you to see is that if you make it to here, if the machine operated, then by the time you get over here, it had to have satisfied this condition, which means that x was 0 or positive. Well, what's the absolute value of 0? 0. And what's the absolute value of a positive number? Itself. And the reason why that's the case is because of this. In the end, the reason for this behavior is that squaring is the post-inverse of square root, but not the pre-inverse. These functions are not inverses of each other. They almost are. And that's why secondary school in essentially every state in the Union more or less pretends that they are inverses. They just don't talk about it. Like, I'm just not going to talk about it. They're not. They're inverses in one order but not the other. In the same way that cleaning up the kitchen is the post-inverse of making a mess in the kitchen, but not vice versa. Any question about this? So this is in fact the case for any even number, any even exponent, which is to say that when n is even, the nth root of x to n, if you do even exponent first, even caret first followed by that same radical, this is absolute value of x. But if you do it in the other order, it's just x. So like this. And it's for exactly the same reasons. That for this order, if you're going to do the nth radical of x, and if it's going to work, then x itself could not have been negative in the first place. And then if you follow that up with caret n, then you just get x back. Whereas when n is odd, no matter what order you do it in, the nth root of x to n is x, and if you compute nth root of x first and then raise that to exponent n, that's also x. So you can almost kind of forgive secondary school, middle school and secondary school, because, well, in a sense, 3 out of 4 times it's x. But not that time. Good. Any question about this? Okay. So now, the question we want to ask is the following. So this is not the question I'm interested in. This is a much simpler question. So which reals have an additive inverse? That's one question. Second question is which reals have a multiplicative inverse? Okay, so I'll stop there. So which reals have an additive inverse? All of them. They all do. So I want to sort of, interpret that as saying, well, addition is pretty easy, because that means that addition in all circumstances can be undone. Adding 7, the undo button for that is add -7, or if you like, subtract 7. Okay. Which reals have a multiplicative inverse? The non-zero ones, right? So now it's all reals except 0. So multiplication is more complicated in that sense because almost every multiplication has an inverse, but not all of them. Because, well, multiplication by 3, the undo button for it is divide by 3. Or if you like, multiply by 1/3. But so if the undo button for multiply by 2 is divide by 2, then the undo button for multiply by 0, if it could be anything, would be divide by 0. But you can't do that. So multiplication is more complicated than addition in that sense. But here's the question, here's the real question that I want to ask. Which functions have a compositional inverse? That is to say, if I give you a function, I want you to be able to come up with a second function, and you wire up those two machines in order. First that one, then the other one, and then the result is the identity function. Okay, so here it is. I mean, this is not the answer, but I think we'll be able to state the answer after looking at it. So suppose that we have this function 1, 2, 3. And with domain 1, 2, 3 and range 7, 8, 9, and that it is wired up in this way. So 1 to 8, 2 to 9, and 3 to 7. Okay, so now I already said it was a function, and it is. But nevertheless, for reasons of exposition, I'm going to say, is this a function? Okay, because strictly speaking, it's a relation, right? If I hadn't already said it's a function. How can you tell that this is, in fact, a function? Everything in the domain has one arrow leaving. So yes, because every element in the domain has exactly one arrow leaving. Okay, so that means that this thing that we've called f is a function. Now I want you to make another one. And the way I want you to do it is I want you to draw the big rectangle, and I want you to draw the little rectangles, and I want you to make their contents the same. So 1, 2, 3 is here, 7, 8, 9 is here. And in fact, I want you to draw the arrows the same, with one exception. I want you to make the pointy bit pointing the other way. So like 1 and 8 are connected, just like before, except now it's 8 is pointing to 1 instead of the other way around. And I want to ask the same question. Is this a function? And again, because we're making the pointiness pointing the other way, that means that the domain and ranges have swapped. This one is the domain and that's the range. So is this a function?
Yes.
Yes, for the same reason.
So wherever the arrows start in these analogies
Mm-hmm.
is the domain.
Right, the domain. So you leave the domain and arrive at the range. All right, so it's a function. Now, just like we wired up the square and the square root, I want to wire up that function and that function. You know, I'm not going to take the time to wire them up in both orders. I'm just going to wire them up in one order. So I'll do this one first and then that one. So 1, 2, 3, 7, 8, 9. 1, 2, 3. This first thing is going to be f. One to 8, 2 to 9, 3 to 7. Okay, so now to wire up the second leg, I've got to look. Okay, for the second function, which I've got to remember is drawn pointing backwards, where does 7 go? It goes to 3. Okay. Then 8 goes to 1. And 9 goes to 2. Okay, so now we got a function here. I have a question. If the input is 1, then what's the output? 1, right? Because as an intermediate step, it becomes an 8, and then after that, it becomes a 1. So if 1 is input, then 1 is output. What if 2 is input? Then 2 is output. What if 3 is input? Then 3 is output. So what is this? This is the identity. This is a conveyor belt, right? An X goes in, and it loudly, saws. X comes out. This is the identity. If you take the time to wire it up in the other order, then when you input 7, 7 will be output. When you input 8, 8 will be output. When you input 9, 9 will be output. So it's the identity in both orders. So, does this F have an inverse? It does. And that's it. Therefore, F has a compositional inverse. So the name for this inverse, the way that you write it out loud, just like the name for the additive inverse of 3 is negative 3, and the multiplicative inverse of 3 is 1 over 3, the name for the compositional inverse of F is F with a negative 1 superscript. So that's its name. And it's pronounced F inverse. All right. So, here's a G. Now, the domain is going to be -1, 0, 1, and the range 0, 1. Now, normally when I'm drawing these arrow thingies, I'm just arbitrarily connecting them, just making something up. But now what I'm going to do, in fact, is I'm going to square it. So what's the square of -1? 1. What's the square of 0? 0. And what's the square of 1? 1. Okay, so is this a function? Yes. For the same reasons as the previous page. Now, I'm going to take this G, and I'm going to do the same thing as before. We're going to write the big rectangle, the little rectangles, all the numbers in the same places, all the connections in the same places, but the pointiness is going to be pointing the other way. And I'm going to ask the same question. Is it a function?
No.
Now the answer is no. Why not? Right, because more than one arrow leaves this element. Therefore, we can say, what about this G? Does it have a compositional inverse? It does not. It does not. Because when we turn this around, it's not a function. Therefore, G does not have a compositional inverse. Okay, so now I can finally put a nice bow on this. All right. Can we agree that if I drew any function whatsoever, if one of the things in the in the range has more than one arrow pointing to it, when we turn it around, the result's not going to be a function. And furthermore, it is exactly the case that when one arrow is always arriving at all of these, when you turn it around, it'll be a function. Well, we have a name for the functions where all of these have at most one arrow pointing at them. Injective functions. This doesn't have a compositional inverse, and that means it is like 0. It's something that can't be undone. You can't undo it, multiplying by 0. G can't be undone. It can't be undone because if you see someone walk away with the 1 candy bar, you don't know if they pressed -1 or 1. You don't know what they did, so you can't undo what they did. So the injective functions have a compositional inverse. Now, in your mind's eye, I'd like for you to imagine the parabola. And I'd like for you to remember that the visual test for injectiveness is the horizontal line test. Is the parabola injective? It is not. Therefore, it's not invertible. We saw that right here. And now, I want you to see the first question that we asked today. Determine if these functions are compositional inverses. Well, I claim that you should be able to tell me the answer is no without doing any work whatsoever.
Because that's squared.
Right. The answer is no.
It'd be a parabola.
Because this thing, when you plot it, does not pass the horizontal line test. Therefore, this thing is not injective. Therefore, it doesn't have a compositional inverse. And therefore, this thing certainly could not be its compositional inverse because there isn't one. Right? Squaring function doesn't have a compositional inverse. Good. So I hope you have a wonderful Wednesday.